All right, good morning. Y'all doing okay? Good, okay. So this is it, last hurrah here. Let's see. Can y'all see that okay? All right, so I've got a couple of things that we need to talk about before we get started here. So I was looking at the final exam. I sent out the review today. So I sent out something for you to look at. And your final is scheduled for Monday, December 11th. I mean, yeah, December 11th at 11 a.m. So I wanted to take a poll of the class right now to see if you would be available to do one of these options. So just, you know, A for the first one, B for the second one, and then C if you just absolutely could not make one of those times. Trying to see if maybe there's a way I can give you a little more time to get ready for the exam. So if you could kind of check your calendar, see if that conflicts, and then take the poll.
I just want to make sure if I pick B, that means I can do Friday.
No, this is just to get a feel for the class. Like, could you make one of those 2 days to take the final instead of taking it on Monday? Does that answer your question or not?
Well, I picked B and it said no on there, but I wasn't sure if B was actually that I could do Friday.
I'm not looking at yes or no on there. I'm just
Okay.
A, B, or C. Who picked D? Okay. So from what I've got, there's only 7 responses so far out of 10. Who cannot do one of those times? Who is that?
I mean, I could, but I'd have to talk to my boss. I'd prefer not to, but it is what it is.
You prefer not to what?
To wait. Like, honestly, I'd take it Monday if I could, but it is what it is.
Yeah. So, you know, I want to be able to give you more time if you feel like you need more time. You know, I'm not going to, obviously I'm not going to move the day and time of the final. You know, if someone wants to take it on Monday at 11 a.m., I will give the test on Monday at 11 a.m. But I wanted to see how many people would do it at a later date if they had that option. And it looks like 6 of you would maybe be willing to. Think about it a little bit more over the class while we go through today. All right. The problem is if I do it, I'm going to wind up making like three different copies of it, 3 different versions of a test. I'm going to have one for your class. I'm going to have another one for my Tuesday, Thursday class, and then I'm going to have another one for whoever does it on Friday. So anyway, it's not easy for me, but you know, Monday's like right around the corner. So we still have a lot of material. Okay. All right. That's it for now. That gives me at least a feel for where we are. Okay. So I started this out here with this equation here, e raised to the I pi plus 1 equals 0. Maybe you've seen this before, maybe not. This is argued to be the most beautiful equation in math, but you know, beauty is subjective. So, you know, not everyone buys into that. But you know, it is pretty nice. It is a nice equation. It's a true equation. And if you look at it, really all it's saying is that, you know, if you subtract 1 on both sides of this equation, all we're really saying is this: e to the I pi is equal to -1, right? That's really what the equation is saying. Now, when you write it this way in red, it's considered to be the most beautiful equation because of this. And we're going to prove this today. I'm going to show this is true. The reason why it's considered to be the most beautiful equation, I'll put it down here again, is because it contains all of the really important numbers in our number system. 0, even though you just look at 0 as being 0, our number system is called, in mathematics, it's called a field. And a field is any set of objects that satisfy a bunch of different they have a bunch of different properties to them. They're called the field axioms. And the first axiom is that any field must have what's called an additive identity. And so 0 is our additive identity. It's anything plus 0 is itself, right? And every field must also have a multiplicative identity. And 1, which also is in this equation, is our multiplicative identity. Any number times 1 is itself, right? Other than, well, 0, no, it works for 0 too, right? If you go 0 times 1, you still get 0. So we have our multiplicative identity in there. We have pi, right? Which is, well, we know it's all connected with circles. We have I, which is the imaginary unit. And I forgot to put E here. Obviously, E is in here. And we know E is important because when we look at the function e to the x, that function e to the x is the only function that is its own derivative. It's a very unique property of that function. So the number E is really important. And then I, the imaginary unit, we don't talk about this much. In college algebra, we do a little bit. But the imaginary unit is the basis for all complex numbers and all of a whole different branch of math called complex variables. So I just wrote down some things about I here in case you don't know. I, by definition, is the square root of -1. So if you square I, you get rid of the root and you have -1. So I is this weird imaginary unit that when you square it, you get a negative number, right? When you square I, you get -1. And then if you cube I, that means you're going to take I squared and multiply it times I. Well, I squared is -1, so -1 times I is going to be -I. And then I cubed would be I squared times I squared, but each I squared is -1, right? So that's -1 times -1, that gives you +1. Then I to the 5th power would be I to the 4th times I, which is I to the 4th we just said was 1. So 1 times I is I. So we're back at I. So we started at I, then we squared it, we got -1. We cubed it, we got -I. We 4th power, we got 1. Then we got I, and we can do the 6th power, we'll go back to -1, then back to I, -I, then back to 1, then back to I. And so this I is what we call in math cyclic. It cycles through. It goes I, -1, -I, 1, and then back. As you raise powers, it just keeps doing that. It's kind of like, you know, -1. When we raise that to the n, that's gonna give us one of two answers. It's either gonna be 1 or -1. Well, I raised to the n is gonna give us like one of 4 different answers, right? It's either gonna be I, -1, -I, or 1, okay? So any number that does that as you raise it to powers is called a cyclic number. Okay, I'm going outside of what we need to talk about, but I will need this. I will need you to kind of understand this a little bit for me to prove this up here. Okay, so I thought that would be a nice thing to show you at the end, that we can actually prove that formula, but we need to get back to where we were last time. And last class, what we were doing was we had started talking about Taylor-Maclaurin series, and I tried to get you to understand that really the only thing that separates functions from other functions is when you look at their Taylor series, the only differences that we have are what the numbers in front are. And we derived a formula. We were able to come up with a formula for those coefficients, for those numbers. And once we did that, we looked at e to the x, and we took a bunch of derivatives and then we plugged 0 in, and we actually found a formula, a power series for e to the x. And we did the same thing for sine x. We did a bunch of derivatives, we plugged in 0, and then we were able to come up with a form. We never got the formula, but we started to get the power series here. So what I want to do is continue from last time, but we're going to do one more function first. And I also have a summary of everything I just kind of said, all right? So given any power series about x equals a, this is what they look like, right? And the c sub n is what's important, but we've established that c sub n with a formula. We did this last class. So when you look at this formula, it says that you're going to take the nth. So if you want to know what c sub 0 is, you would go put a 0 here and a 0 here. So 0 here means the 0th derivative of the function. Remember, the parentheses around the end means derivative. So the 0th derivative of a function means don't take its derivative, all right? So that's just the original function. You plug in a and you divide by n factorial, right? That was the very powerful formula we came up with last time. So a Taylor series, okay, this is a definition. A Taylor series at x equals a is that power series formula with the C sub n just being replaced with that, okay? So all we're doing is we're taking this and we're sticking it in right there. And when we do that, here it is, right? We get what's called a Taylor series, all right? It's called the Taylor series about x equals a. Now, if I start plugging in values of n, so I start at n equals 0, I plug in 0 here, 0 here, 0 here, this is what I would get. Ah, shit, I messed this up. I messed up. Okay, each of these, sorry, each of these are not x. It's x minus a. I apologize. This is x minus a to the 0 plus, and then this thing, x minus a to the first plus x minus a squared plus x minus a cubed plus, okay. Sorry about that. So when you plug in 0, you get the 0th derivative of the function at a divided by 0 factorial x minus a to the 0. Then you plug in 1. The first derivative, right? First derivative of this function at a over 1 factorial x minus a to the first power, and then so on and so forth. Are there any questions about that? So that's what a Taylor series is. So if you're ever given a function and asked to find the Taylor series at some value, let's say x equals 2, you're going to wind up taking a bunch of derivatives, and then you're going to be plugging 2 into all those derivatives, and then you're going to be writing out this series. Now, it comes up very often that we want to do a Taylor series at 0, at x equals 0. That's the most common Taylor series out there, is when you let x be 0. And when you do that, if you let x be 0, it's still a Taylor series, okay? But we have another name for it too. It's called a Maclaurin series. So if you let x be 0 in this formula, then we call it Maclaurin. And the formula changes because this a here and this a here, they get replaced with zeros. And so that a right there becomes 0, and then now it's x minus 0, so it's just x to the n instead of x minus a to the n. And when you plug in values of n into this, right, n equals 0, 1, 2, 3, you get this. All right? So if somebody says Maclaurin series, find the Maclaurin series, then you have to know that means x is 0. A is 0, sorry. All right? You need to just know that. Now, it's important to note that, you know, we're starting with a function and we're creating its Taylor series, right? Or its Maclaurin series. It's important to understand that in order to do that, you're going to have to be able to take derivatives, a bunch of derivatives, right? And you're going to have to be able to plug a number into those derivatives. So we have to know a whole hell of a lot about the function. Like we've got to know a lot about the derivative of the function at a particular value. So you may be asking yourself, well, why? What's the use of doing a Taylor series or a Maclaurin series of a function if we have to know so much about that function? Well, I understand, I agree. We do have to know a lot, but we only have to know a lot about the function at a single point. See, this is what I think is amazing about this. It's like you have a function, okay, and whatever it looks like, if you go to this a right here, in order for me to figure out what all of the rest of the function looks like, the yellow part, what I need to know is almost everything about the function at a. I need to know the function's value at a. I need to know the derivative of the function at a, the second derivative at a, the third derivative at a, the fourth derivative at a. Does that make sense? It's like I've got to know everything about what's happening at that point, and then I can extract from that the rest of the function, which is pretty amazing if you ask me, okay? Does that kind of make sense? We don't get it for free, okay? We don't get the Taylor series and Maclaurin series for free. There's a cost to it. We have to know a lot about the derivatives, but only at a point. Okay. I will provide these notes to you. I'll send these out to you later. All right, so here's the first example that we're gonna do. We wanna find the Maclaurin series for the given function using two methods. The first method is we're going to derive it, and then we're going to go cheat and we're going to use our Maclaurin series table. All right. So what is the Maclaurin series for cosine? So what we know is that this should be equal to the sum n equals 0 to infinity of the nth derivative at 0 over n factorial x to the n. Okay, that's what this should be. All right, now that's the Maclaurin series formula, right? That's the formula from the previous page right here. That's this. That's what a Maclaurin series is. Okay, so the approach that we're going to use for step one, this is method one, sorry, we're deriving it, is we need to first figure out what these derivatives look like. Okay, so I'm going to start out, what is the 0th derivative of that function? So that means we look at our function cosine x, we don't take the derivative, so it's just cosine x. And then we take the first derivative of the function, and that is negative sine x. And then we take the second derivative, and we get negative cosine x. Then we take the third derivative, and we get, what's that? Sine, right? Fourth derivative, cosine. Okay, so we're back to cosine, aren't we? So now it's just going to keep repeating, isn't it? It's going to go cosine, negative sine, negative cosine, sine, cosine, right? That's what's happening as we go down here. You with me? Okay, now what I'm going to do, because it's a Maclaurin series, I'm not interested in these derivatives, like general derivatives. I want to know what their values are at a particular number. And the number I want to know is 0 because it's Maclaurin, right? So I'm going to go next to this and I'm going to say, okay, what's the 0th derivative at 0? So we're plugging 0 into that. Cosine of 0 is 1, right? Then we do the first derivative at 0, and that's going to be negative sine of 0, which is 0. Then the second derivative at 0, which is negative cosine of 0. Cosine of 0 is 1, so that's negative 1. You just stop me if there's any questions. Sine of 0, which is 0. What's going to happen now?
It's going to start over.
Yeah, it's just going to repeat. Okay, so now the next one's going to be 1, then 0, then negative 1, then 0, then 1, then 0, then negative 1, then 0, right? That's what's happening. All right. So I think the easiest way to do this now is to write out this thing. Okay, I'm going back up to this right here. Let's write that out. Let's plug in n equals 0. We're going to have the 0th derivative at 0 over 0 factorial x to the 0 plus, now let's replace all our n's with 1. The first derivative at 0 over 1 factorial x to the first power plus the second derivative at 0 over 2 factorial x squared plus the third derivative at 0 over 3 factorial x cubed. I don't know, maybe I'll need more. Maybe I'll need more than that, but let's just start with that, okay? Plus dot, dot, dot. All right, you ready? That should be equal to, all right, what is the 0th derivative at 0? Well, that's this, right? Which is 1. Okay, so that's going to be 1 over 0 factorial x to the 0 plus, okay, now we need to know what the first derivative at 0 is. That's the first derivative at 0, and that's 0, right? So that's going to give me 0 over 1 factorial x to the first power plus, okay, now we do the second derivative, right? That's where we are. We're going to do the second derivative at 0, which is this one, which is negative 1. So that's going to be negative 1 over 2 factorial x squared. Any questions? Next one. Third derivative, now we're at this one, that's 0. So 0 over 3 factorial x to the third, plus the next one would be this 1 now, right? So 1 over 4 factorial x to the fourth. Should I keep going, or do you see the pattern? You'll see it. It looks like all the odd powers are gone, right? Everything that has odd has 0 in the numerator, and that's going to kill it all off. And then the even powers are there, but they keep alternating. Like we're going to get a 1 or negative 1, right? Depending on where we are. So let me see. Let me write this out. If we go, let's see, this first term right here, what is that equal to? Be careful. What's that equal to? Remember, what's 0 factorial?
1.
1. Okay.
So the whole thing equals 1.
That's just 1. Okay, so that's 1. And then this second piece is gone, right? This one's gone because 0 over 1 factorial is 0. So that's gone. The next piece is a negative, right? So I'm going to put minus 1 over 2 factorial, 1 over 2 factorial x squared. Okay, and then that one with the cubed on it's gone because it had a 0. So now I have a plus 1 over 4 factorial x to the fourth. Can you predict what the next one's going to be then?
Minus 1 over 6 factorial x to the sixth.
Yep, 1 over 6 factorial x to the sixth. And then we won't have a 7th power, right? There won't be a 7th, even though it'll be gone. But the next one should be a positive 1. 1 over 8 factorial x to the 8th. The next one will be minus 1 over 10 factorial x to the 10th. Plus dot, 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 I'm out of room. There it is. That's the Maclaurin series. That's the Maclaurin series for cosine. So I would like for us to rewrite this now as in sigma notation. Let's start at n equals 0 to infinity. I want us to create this series. So the first thing we want to notice is that this is an alternating series, right? It's going plus, minus, plus, minus, plus, minus. So be careful here. I'm going to write negative 1 to the n. Now, I know you might be tempted here to put n plus 1 because that's what usually we started with to make it start positive. But remember, we're starting our index at 0. So if you plug 0 into this, 0 power here, negative 1 to the 0 is going to be positive 1. And then if you go let n be 1, now you have negative 1 to the first power, that'll be negative 1. So negative 1 to the n is going to create this positive, negative, positive, negative. Do y'all see that? Do y'all agree with that? Okay, what else do I have here? How about these denominators? Let's look at all these factorials. This first one was really a 0 factorial. So 0 factorial, 2, 4, 6, 8, 10, right? Those are even numbers starting at what?
0.
0. But remember, we're also starting our index at 0, not at 1. So I need down here, how about 2n? That'll jump by 2 each time, right? 2n, and just in parentheses, factorial. Just check it for yourself. If you let n be 0, you get 0 factorial. If you let n be 1, you get 2 factorial. If you let n be 2, you get 4 factorial, right? Okay, and then what about x? We have x to the, well, that first one had an x to the 0, didn't it? X to the 0. That's really what's here, right? X to the 0. So x to the 0, x squared, x to the fourth, 6, 8, 10. So evens again, right? So x to the what?
2n.
2n. That's it. That is the Maclaurin series for cosine. We're done. Now, let's do it the second method. Second method, we go to our formula sheets and we look at our Maclaurin series and we look at cosine and we see it right here. right? That's it. That's the Maclaurin series. That's exactly what we just got. -1 to the n, x to 2n over 2n factorial. So on your review that I sent you, you'll see here, there's a couple of problems. Where is it? Right here, number 7. Find the Maclaurin series for e raised to -2x. And I say you must derive this series. You may not use the table. And what that means is you've got to list out all the derivatives, and then you got to plug 0 into those derivatives, and then you got to do exactly what we just did. Okay. All right, and then this one is find the Taylor series for this function at a equals 2. So this, you're going to have to use the other formula where you have an a in there now, right? A is actually 2, and you must derive this. So you have to run through all the derivatives listed out. Kind of messy. All right, questions? Okay, so let's go back to last class. Last class, we had done the same exact thing for sine. I had given you sine x. I said, let's use that formula. Now, at this time, I couldn't call it a Maclaurin series because I hadn't defined it yet. But we did the same thing. We did this last class. We did the Maclaurin series. We had sine x. We listed out all the derivatives. We plugged 0 in. And when we got that, we came up with this series right here, right? It was all the odds. And I mentioned that's why we call sine an odd function, and then cosine's even because it has all even powers of x. What we didn't do is write this in a sigma notation. So if we wanted to do this, we would still want it to alternate, starting positive then negative, positive then negative. But our factorials are odd numbers, starting with 1, because this is a 1 factorial under here. So to do that, I would do 2n plus 1 factorial. That would start me at 1, and then it would jump by 2 each time. So I go 1, 3, 5, 7, and then x to the same thing, 2n plus 1. I hope that that's clear. Are there any questions on that? No? We're good? And that's on your Maclaurin series table. All right, right here, sine, boom, there it is, -1 to the n, x to the 2n plus 1, 2n plus 1 factorial. There it is, boom, 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 boom. Those are all the terms, okay? So let's do something a little harder, okay? Let's do f of x equals, let's try cosine of pi x. Same thing. Let's find Maclaurin. Okay, let's find the Maclaurin series. And you can't use the table. You're not allowed to use the table, okay? You've got to derive it. So let's start listing out derivatives. I'm going to go a little faster now because we've got one of these under our belts here. The 0th derivative is itself. All right. First derivative. What's first derivative? Careful.
Negative sine of pi x.
Negative sine. I agree with that part. Hold on. I agree it's negative sine of pi x, but don't forget chain rule. You then have to take derivative of what's inside, which would spit a pi out, wouldn't it? So you're actually going to have negative pi sine pi x, right? Now take the second derivative. I'm going to skip a line to give myself some more room. The second derivative of this. Now the negative pi that's in front, right? This negative pi that's in front is a constant. So it's going to come for the ride, isn't it? But you do have to take derivative of sine of pi x, which would be
Pi cosine of
pi. So you get another pi that pops out, right? And then cosine of pi x, but you already had a negative pi out there. So wouldn't this be negative pi squared cosine pi x? Does everyone understand where the pi square came from?
Wouldn't that just be pi squared cosine pi x because it'll be a negative cosine?
No, because what you did when you took derivative of this, you had a negative pi, right? And then times, now you took derivative of this right here. And the derivative of that is cosine of
Cosine.
pi x times pi. So you're not squaring, when you multiply these two, you're squaring the pi's, but not the negative.
Sure.
Yep, okay. All right, so now the third derivative. So aren't we gonna keep on getting pi's popping out each time? So am I gonna have a positive or a negative this time though? Because when you take derivative of cosine, don't you get a negative sign? But we already have a negative out there. So what, pi cubed sine pi x? Right? What would the next one be? Fourth derivative. Wouldn't it
Pi to the
stay?
fourth cosine x.
Yeah, it would stay positive. Pi to the fourth cosine pi x. And then we keep going. Let's do one more. Fifth derivative at x. Now we're gonna get a negative again, right? Negative pi to the fifth cosine pi x. All right, I think that's enough for us to establish what's going on. Now we need to plug 0 into these.
Would the fifth derivative be the sine to pi?
Oh
x?
yeah, I don't know why I did that, sorry. Sine, thank you. So the 0th derivative at, what are we plugging into this? At, where are we plugging, what? What are we plugging in? 0, right? Because it's Maclaurin. All right, so 0th derivative. And when we do that, let's see, cosine of 0 is 1. Okay, so that's 1. When we do the first derivative at 0, what happens? Well, any of these that have sign are going to be gone, right? Any of these that have sign are going to be zeros. So that's going to be 0. All right, let's be careful here. The second derivative at 0. All right, so when we plug 0 into this, we have to do cosine of 0, right? Cosine of 0 is 1. But we still have what out front? Negative pi squared, right? Negative pi squared. The next one will be 0. What's the next one going to be?
Pi fourth.
Pi to the fourth. Okay. What's the next one going to be? It has a
0.
sign in it, doesn't it? So that would be 0. What would the next one be? Do you see the pattern or no?
Would be negative pi to the sixth.
Negative pi to the 6 would be the next one. Next one after that, 0. Next one after that,
Pi to the 8th.
pi to the 8th. So we want to do this enough to establish a pattern, okay? We want to establish a pattern. And now let's go ahead and write this series out for this. Now, when I write this, let's see if you can keep up with this. I'm actually going to take this right here. Right, this is what I'm going to use. See if it'll let me slap it. I don't know where. I'll slap it right here if it'll let me. Squeeze it right in there. Okay, so that's what I'm about to do, right? I'm about to do this. So it'll be this first number, right? The yellow number here over 0 factorial x to the 0. So 1 over 0 factorial x to the 0 plus nothing, right? The next one's not going to be there. So I'm not even going to put anything, right? This one's gone, not here. Next one would be it's going to be a minus, isn't it? Minus pi squared over 2 factorial x squared. Am I going to have the third one? No, right? No third power. Okay, so next one will be a plus, and then it'll be pi to the 4th over 4 factorial x to the 4th. And then we won't have a fifth power, but we'll have a minus pi to the sixth over 6 factorial x to the sixth. Then we won't have a seventh power, but we'll have an eighth power, pi to the eighth, 8 factorial x to the eighth. And now what we can do is put it in sigma notation. All right. It alternates, so I need -1 to the n. On the bottom, we need the even powers of factorial, 2n in parentheses factorial. But what goes here? Because don't we have pi's in there now? Right? But do you notice that the pi's and the x's are both raised to the same powers? Aren't they? Just so happens to be the case. So couldn't I just do this then? Pi x to the 2n. Couldn't I do that? I mean, it's pi squared x squared, so that should work. Pi to the fourth, x to the fourth, pi to the sixth, x to the sixth. And I put the 2n to give me the even powers, right? That's it. So I want to show you, if we were able to use the Maclaurin series table, right? If you were able to do that, I want to show you how easy this problem would be. See, we're taking cosine, we're plugging in pi x, right? So if I go to the Maclaurin series cheat sheet table here, if I were to replace that x with pi x, then this would become pi x raised to the 2n, right? And that's it. That's what we have. That's too easy, right? That's too easy to do that. But that's how it's done, right? That's what makes the Maclaurin series table so beautiful, is that if you have something like, you know, cosine of any expression, you just plug that expression in here. And that's the series for it. All right, let's do another one. This one's gonna be harder. F of x is x sine x, and I want Maclaurin. Okay, let's try it. I need derivatives, right? Zeroth derivative of this function is itself. All right. First derivative of this function. Do y'all see this is going to start to suck? Because what do I have to do to take that derivative? Little product rule there, right? Little product rule. So the derivative of that should just be sine x plus x cosine x. I'm going to trust that you could do that, right? Just a little product rule. And now we're going to take the second derivative, and that's going to not be great. I can do derivative of the sine as cosine, but then when I take derivative of this x cosine x, I have to do a product rule here, don't I? So I have to do a little product right there. So it'll be, let's see, plus cosine x, and then won't it be minus x sine x? Because when I take derivative of cosine, I'm getting negative sine, and then I hit it with x. So everything in blue here is that product rule. We good? I'm actually going to clean this one up a little bit because I notice I have cosine x plus cosine x. So I'm going to put those together. And when I put cosine x plus cosine x together, I get two of them. Okay, so that's my second derivative. Third derivative. This is looking pretty shitty here. Okay, let's see. Derivative of 2 cosine x is -2 sine x minus, now I need to take derivative of x sine x, right? Haven't we done that already? Didn't we take derivative of x sine x? We did that earlier, didn't we? So I'm just going to point out that what's up here in parentheses and black parentheses is the derivative of that, isn't it? So I'm going to slap that right here. And you have to have it in parentheses because that negative sign right here has to distribute through. So here's where I'm at. Let me distribute that minus through. So if I have -2 sine x minus sine x, isn't that -3 sine x? And then minus x cosine x? Do y'all need me to like slow down or stop or anything, or are y'all good? Fourth derivative. -3 cosine x, that's the first one, and then minus, and now I take derivative of x cosine x, but didn't I do that already? I did that right there, x cosine x, when I took its derivative, I got that right there, didn't I, the yellow? So I'm gonna put that in parentheses, don't forget, you gotta get that in parentheses because that minus, that's cosine x minus x sine x. And now let's distribute. Man, I'm starting to see a pattern. Are you seeing a pattern? Maybe we should do one more. -3 cosine x minus cosine x is -4 cosine x, and then this minus minus becomes plus. Okay, fifth derivative. Fifth derivative, lost. Okay, 5 sine x. And then plus x sine x. I already did that derivative earlier. That was sine x plus x cosine x. That was up here, the very first one. And I can put that together and that'll give me 6 sine x plus x cosine x. All right, I'm going to highlight in blue what our answers were. So that was the 0th derivative. Here's our first derivative. Here's our second derivative. Here's our third derivative. Here's our fourth derivative. And here's, wait a minute. Did I mess something up? I did mess something up. Y'all see what I did?
Did you forget to distribute the?
No, I made this, hold on. I made this a 5. And I'm not sure why I made that a 5. I was taking the derivative of this, right? The derivative of that should be +4 sine x, not +5. Do y'all see that? Okay. So change that, and that's going to change that. So this is a positive, I did it again. +4 sine x. And now when I add those two together, I get 5. Okay, so that the pattern wasn't, pattern got messed up there. Right, because I have like 2 of these, -3, then I've got -4, then I've got 5. Do y'all see that? It's like going up by 1 each time. All right, now we've got to plug in 0 into all these. Okay, so what is the 0th derivative at 0? I'm plugging in 0 because it's a Maclaurin series. Oh, that's nice. That's 0, isn't it? When I plug 0 in to this for x. Okay, what happens when I plug 0 into this one? So for the first derivative, I get 0 again, don't I? Sine of 0, 0, 0 times that, 0. Okay, so 0. All right, let's do the second derivative at 0. We finally get something, don't we? What do we get?
2.
2. Okay. All right, what about the next one? Third derivative. 0. What happens? That's 0, and then 0 times who cares, right? This is all 0 again. Right? What about this one? The fourth derivative at 0, what are we getting? See,
Is that
cosine,
-4?
-4, right? -4, because that right there is just going to be, all right, that's going to go to 0. So that's just -4. And then what's the next one?
0.
0. And then predictions on the next one?
6.
6. Predictions on the next one?
0.
0. Next one?
-8.
-8. Do y'all see that this is going to keep happening? It's like 2, 0, -4, 0, 6, 0, -8. And it's all really, it's always coming from this. The thing you need to realize is that what comes out is always being dictated by this thing out front. The thing in the back here is always going to go to 0 because it's x times something, right? X times something. So those are always going to go away. And so if we look at those numbers, the way they're counting, yeah, okay. You ready to write out the Maclaurin series then? Let's write it out. Shoot. Yeah, I'm gonna just try and squeeze it in here because I'm gonna run out of room. I'm gonna try and squeeze it right here. So remember, the formula is the 0th derivative. Do I need to write it out again or no? I'm talking about this formula right here. It's the 0th derivative at 0 over 0 factorial x to the 0. First derivative at 0 over 1 factorial x to the 1. That's what I'm about to do, right? Okay, what is the 0th derivative at 0? Well, that's 0 over 0 factorial x to the 0. Plus, now, the first derivative at 0, which is 0, over 1 factorial x to the 1. Plus, now the second derivative at 0, which is 2 over 2 factorial x squared. Plus, now the third derivative at 0, which is 0 over 3 factorial x cubed. Plus the fourth derivative at 0, which is -4 over 4 factorial x to the 4th. Plus 0 again over 5 factorial x to the 5th. Plus, we said the next one would be 6 over 6 factorial x to the 6th plus ... I'm out of room. But I think I've established the pattern. Any questions? I'm going to try and write this in sigma notation. Gone, gone, right? Those are gone. So here's what I have. I have that that's equal to 2 over 2 factorial x squared minus 4 over 4 factorial x to the 4th plus 6 over 6 factorial x to the 6th minus, no, 8. I'm just going off the pattern now. 8 over 8 factorial x to the 8th. The next one should be plus 10 over 10 factorial x to the 10th plus ... which equals sum n equals 0 to infinity. All right, let's see if, who wants to make me happy today and tell me what this formula is going to be? Not all at one time, please. Please. Make it alternate first.
-1 to the n.
To the end. Okay, that gets our alternating. Take care of my denominators. Take care of my factorials. How are you going to create the factorials on the bottom?
2n factorial.
Close. Where do they start?
2n plus 2 factorial.
2n plus 2. See, if you just do 2n, it's going to give you a 0 factorial first, but we want a 2 factorial, right? So 2n plus 2 factorial, okay? And then what about all those? Aren't the numerators just 2, 4, 6, 8, 10, right? Aren't those also just even starting at 2? So I could just go up here, 2n plus 2. And all I have left really is the x's. X to what power?
2n.
2n plus 2.
2n plus 2 again, right? 2n plus 2, because basically everything here starts at 2 and it's even numbers. Just this is what the series is, all right? What do y'all think? That's a pretty cool problem, right? I think that's cool. Now, could we have done that using the Maclaurin series table? Could we have cheated? could we have said, okay, you got f of x equals x sine x, right? But we know what sine x is. Don't we know what sine x is, everyone? Isn't sine x the sum n equals 0 to infinity, -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial? Isn't that what sine is? We just did that problem, right? Sine, didn't we come up with that formula? So what would happen if I take the x that's in front and multiply it in here? So let's just move that x inside and make it be times x right there. Couldn't you put these two x's together? So you'd add the exponents, wouldn't you? So you get sum n equals 0 to infinity, -1 to the n, x to the what? 2n
Plus 2.
plus 2, okay, over 2n plus 1 factorial. Wait a minute, that's not what we have. It's not what we have. Did we mess up? We didn't. Does anyone see it? How could you rewrite that? Think about this. How are we rewriting this when we were doing ratio tests? What do we always do with that? We rewrote that as what?
N times n plus 1 factorial.
Other way around, n factorial times n plus 1, right? That's the way we did it. So we took whatever was here, we put it in parentheses, and we subtracted 1 from it, right? That was a property. So couldn't you write 2n plus 2 factorial as 2n plus 2 times 2n plus 1 factorial, right? It's this number, and then times this number minus 1 less than it, right? Factorial. Isn't that what that is? Do y'all believe that or not? So if I rewrite that as 2n plus 2 times 2n plus 1 factorial, the 2n plus 2's cancel. And then I have this. Maybe it would have been easier had we realized that earlier, like, nah, I'm not even gonna get into it because we're halfway through the class already. Okay, what do you think? Shortcut, that's pretty nice, right? Because that means you can take a function like this and you can very quickly write its power series down, right? Very quickly. And then just start plugging in values of n and you would spit this out up here, okay? All right. Are y'all, I don't know. I feel like I need to do more examples. I need to show y'all a Taylor series. I do. I need to show y'all a Taylor series. So let's do this. Let's do f of x equals e to the negative x. Let's find the Taylor at x equals 1. Let's make it, yeah, no, let's make it 2, just to make it more interesting. All right, you ready? Derivative time. 0th derivative is itself, right? You know what, can we do something? I just want to make this one more like the level of what you'd see on the test. Can we just change that negative x to, let's just go negative 4x. Let's go negative 4x. Because that'll make something more interesting happen. When we take our first derivative, because we have a negative 4x, what's going to pop out in front of this?
A 4?
A negative 4, right? A negative 4, because we have to take derivative of what's up on top, which is negative 4. So we're going to have negative 4 e to the negative 4x. And what happens when we take derivative again?
It'll be 16 e to the negative 4x.
That's right. It'll be, I'm going to write it down, negative 4 times negative 4 again, e to the negative 4x, which will be, yes, I agree. It'll be 16 e to the negative 4x. Yeah. Okay, next time we get third derivative. Okay, I'm going to hit it with another negative 4, right? Again. So instead of writing it like, I'm going to start writing it this way. It's negative 4, but it's now the third time I'm having to multiply it times itself. So I'm going to go negative 4 to the third. This was negative 4 squared, right? This was negative 4 to the first power. E to the negative 4x. I'm not even going to figure out what that is. I don't care. The fourth derivative, I'm going to have negative 4, another negative 4, so negative 4 to the 4, e to the negative 4x, and so on and so forth, right? I think you see the pattern, yes? All right, let's now plug in, but what are we plugging into these?
2.
2, not 0, right? So what is the 0th derivative at 2? Well, that's e to the negative 8. Isn't it? Plugging in 2 into the original function for x. What is the first derivative at 2? Well, that's negative 4. I'm going to say negative 4 to the first power. I know you're not going to like that, but then e to the negative 8 again, like that. The next one will be negative 4 squared e to the negative 8. Next one will be negative 4 to the third e to the negative 8. Next one's negative 4 to the fourth e to the negative 8. Now we haven't done this before, okay? We haven't done this before, but this pattern is actually really easy to pick up on. I think it is. Would y'all agree with this? I'm going to do a different color because we haven't done this. Would y'all agree that the nth derivative at 2 would just be negative 4 to the n e to the negative 8? Do y'all agree? That's a pattern that I'm seeing. In fact, does it work for this first one? This would have to be negative 4 to the 0, which it is, right? It is. That's really nice. Now, we couldn't do this before with the sine and cosine. We couldn't do that because every other one would cancel out and go to 0. But this one, there's a nice pattern going each time. So because of that, watch. When I go to rewrite this, I'm going to use this formula. I'm going to use the Taylor. This is what Taylor is. That's what a Taylor is, right? You plug in A here and A here. But the reason why I did this right here, this part, do y'all see that that part right there is actually exactly just this? It's a formula. Instead of me writing out all the pieces like we've been doing, I'm just going to go straight to this formula and go sum n equals 0 to infinity. That part in yellow, which I know is negative 4 to the n e to the negative 8 over n factorial x minus 2 to the n. So the part in yellow came from the fact that I was able to establish a pattern in this and come up with a generic formula for it. And then I just slapped that generic formula in here. There it is. Now, if I wanted to, I could start plugging in values of n and write out the pieces, right? I could start doing that. Do we have any questions? All right. Let me bring that old test back up, or that review here. Taylor series. So the one that I give you, so here's a Maclaurin series, very, very close to what we just did a second ago, but this is a Maclaurin series, so it's even easier because you're plugging in 0 for x. This one though is going to be a bit of a challenge. And I would recommend that when you do this problem on the review here, oh, is my thing not open? Right. Strange. Oh, I'm trying, oh, there it is. Try it one more time. Really weird. Okay, it's acting very strange. All right, so here, when you do that, I would look at that as x to the negative 2. X to the negative 2. And then start doing your derivatives. Right? It's going to get ugly. It's going to get weird, but try it out. Number 14 in the homework is like that problem. Number 14 in the homework, which I know I do on video. Okay. All right. Where are we at? Are y'all ready to see the most beautiful equation? Y'all ready to see that? Okay. Let's do that then. So the most beautiful equation, whatever, we're not going to argue about it. I have to show you this, okay? If I can show you that, do you agree? Do you agree that that's, if I can show you that that equals -1, you'll be happy? Yeah? Okay. So now, here's what I'm going to do. I'm going to figure out what e to the I pi is. All right? But I'm going to rewrite e to the I pi using its Maclaurin series. So here's e to the x. E to the x, here's the Maclaurin series. It's 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial. That's what e to any power is. But for us, what do we have? What's our power? It's not x, it's what? I times pi, right? So I'm just going to go and I'm going to replace all of these things here, all of these x's with I pi. All right. Now, if you don't believe that this is the Maclaurin series for E, if you don't believe that, then all you have to do is go back to your notes because we did that. We did that at the end of class last time. There it is right there. We did that Maclaurin series for e to the x and we came up with this formula right here. So if you don't believe it, then go look at your notes from last time. All right, so y'all ready? I'm going to do it. So this should be equal to 1 plus I pi over 1 factorial plus I pi squared over 2 factorial plus I pi cubed over 3 factorial. I'm going to go quite a few of these. I pi to the 4th over 4 factorial plus I pi to the 5th over 5 factorial. Let's go maybe 2 more. I pi to the 6th over 6 factorial plus I pi to the 7th over 7 factorial. I'll do one more. I pi to the 8th over 8 factorial. I probably don't need all those. All right, good. Next thing. I'm going to go ahead and raise these things to these powers. Okay. So the first thing I have is 1 plus. Okay, this one is just I pi over 1 factorial. The next one is I squared times pi squared over 2 factorial plus I to the 3rd times pi to the 3rd over 3 factorial plus I to the 4th times pi to the 4th over 4 factorial. Sorry, I know this is tedious, but I hope it'll be worth it at the end. Okay, I'll stop there. If we need more, we can get more. All right, now go back to when I started class. Do you remember I said that these powers on E mean something? So I is I, and then we have -1. That's what I squared is. I cubed is -I, and then this is I. So here, I'll bring this. That way we can use that. Okay, so this becomes 1 plus I pi over 1 factorial plus, okay, what was I squared? This is I squared right here. This is I cubed. This is I to the 4th, okay? So I squared is -1, isn't it? Right? So watch what I'm doing. I'm just gonna make a -1, so I'm gonna change that plus to a minus. And that would be pi squared over 2 factorial. Very important that you see that I squared became -1 and I just made that a minus here. Good? What's I cubed? I cubed is just -I, isn't it? -I. So that's going to be minus I pi cubed over 3 factorial. So I just moved the minus out front. I changed the I cubed to I, right? Because it's becoming -I. Next one. Okay, what's I to the 4th? 1, right? So that's just going to be pi to the 4th over 4 factorial. What would be I to the 5th? Just go around the circle, right? This is 2nd, 3rd, 4th. I to the 5th would be just I, right? So this is just going to become plus I pi to the 5th over 5 factorial. All right. I think I need a few more. Let's see. I to the 6th. What would I to the 6th be? So this is 2, 3, 4, 5, 6. Wouldn't that be -1? So negative pi to the 6th over 6 factorial. What would the next one be? We just did -1. So the next one would become -I, right? -I. So -I pi to the 7th over 7 factorial. I'll stop there. Plus ... Okay, so here it comes. This is the badass part right here. All right. Everything in green doesn't have an I in it, right? Everything in green does not have an I. Everything else does. So what I'm going to do is I'm going to reorder this. This is going to be 1 minus pi squared over 2 factorial plus pi to the 4th over 4 factorial minus pi to the 6th over 6 factorial plus ... Okay, that's everything that's in green. There's a pattern to that. The next one would be plus pi to the 8th over 8 factorial and so on and so forth. Now, everything in blue has an I, doesn't it? Everything there has an I. So what I'm going to do now is I'm going to say plus, I'm going to factor the I out of everything in blue. So if I take all the I's out of this, what would be left on this first one? If the I's gone, it would just be what?
Pi over
1
factorial.
factorial. And then what would the next one be? Minus, right? Minus pi cubed over 3 factorial. Next one, plus pi to the 5th over 5 factorial, minus pi to the 7th over 7 factorial, plus ... All right, bonus points. 2 points on the final for someone who can tell me what the hell we are looking at there. 2 points on the final, but you got to answer it in the next like 20 seconds, 30 seconds. Can somebody tell me what this is? No?
Is
Okay,
it just all
quite
the
the
evens?
bonus. What's that?
Is it just all the evens? Is that the answer you're looking for?
Yeah, what does all the evens make you think?
Like even series, even powers.
Cosine.
Like
It'll be alternating, so it'll be -1 to the n. The bottom will be to the 2n.
Okay, bonus is over. All right, but y'all are on the right track. You said all the evens, and I heard someone say something. I think it was Ross.
It looks like the cosine and the sine functions.
It looks like the cosine and sine series, don't they? Remember, cosine was all evens. So what was the cosine one? Let's go back. We derived it. Well, I guess we could look at our own formula. We don't even need to go look at the cheat sheet. We can just go look at ours because we derived it ourselves. Right here. Here was cosine. Wasn't it 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4th? Do we have this? It's freaking close, right? It's 1 minus 1 over 2 factorial. There's no x's here. But what are the x's? It's actually that formula right here. Go ahead, Peggy, was that you?
Instead of the x, it's pi.
It's just pi's, right? All of these x's are replaced with pi's, which means what we're looking at right here
Cosine of pi.
is cosine of pi plus I times, now what are we looking at here?
Sine of pi.
Sine of pi, so times sine of pi. All right, everyone. Do you know what cosine of pi is?
-1,
-1.
-1. Do you know what sine of pi is?
0.
0.
0. Which means that e to the I pi is -1. I can't see how you could possibly ever show that without power series. There's other ways, but all right, so that's pretty bad. Nice, beautiful. All right, you ready? We're gonna move on. We have more time. We have a few more things that I want to talk about. So before I forget this, I will be in touch with y'all soon in the next day or two through email, just to kind of give you updates on what options I'm going to give you for the final, you know, if you want to take it later or something. I need to think about it. Everyone mentally prepare to take it Monday. Okay. But I've got to see how I could logistically figure out how I can offer it later to people. I will follow up with that. I'm also going to give you a link to a couple of videos on lectures that we are not going to be able to cover. And what I'm going to do is I'm going to treat those as bonus questions on the test. However, I know I've talked to some of you about, you know, you want to replace your lowest grade with whatever you get on the final. I really want to try and treat these bonuses as a way of bringing your past grades up. So it's like, if you're happy with where you are in the class, you don't need to watch these videos. You know, you can just focus on the material that's going to be on the test. But if you're looking for bonus, if you're looking for ways to bring your grades up, then you're going to need to go invest a little time into watching some of these lectures. All right. It's going to cover parametric and polar. So on the review, because I know I won't get to it today, on the review, the last problem, number 12, that's a bonus. That won't be on the test as a test question. That'll be on a bonus question. All right. And this one, this problem number 11 is actually just like number 4 and 5. It was a bonus question on a previous test. So you're just running a ratio test on that. It's just a complicated ratio test. That's why it's at the end. So from what we can see here, you can do everything here except 9, 10, and 11. All right. I mean, sorry, 9 and 10 are the only two that you really don't know how to do at this point. So let's look at number 10 first, because you actually do know how to do this. You just didn't know you know how to do it. All right. So I'm going to show you how to do that problem. So if we want to do the integral from 0 to 1 of cosine of x cubed, we cannot integrate this, all right? So the instructions here said, estimate this integral using the first 4 terms of the Maclaurin series. So what we'll do first is we will figure out what cosine of x cubed is using its Maclaurin series. So the Maclaurin series for cosine, I'm going to go grab it. So we have it. Here's the Maclaurin series for cosine. Get off of there. Get off of there. This is very strange that this is not working. Why? My little screen capture thing is not liking me. Try to. I don't have time for this shit. I just don't have time. So you're going to need to, no, this is our Maclaurin for cosine, right? So we have x cubed, so I'm just going to replace that with x cubed, that with x cubed, that with x cubed, right? That's all I'm going to do. So let me do that. Okay, so what was it again? It was 1 minus x squared over 2 factorial, but this is going to be x cubed squared over 2 factorial. And then plus, it was now going to be x to the 4th over 4 factorial. So for us, it's going to be x cubed to the 4th over 4 factorial. And the next one will be minus x cubed to the 6th over 6 factorial plus dot, dot, dot. I'm only going to use the first 4 terms because the instruction said just use the first 4 terms. Anyone have a question on what I'm doing here? Isn't that really nice, easy way to convert this over to something? I mean, you're just replacing that. Okay, this is going to become 1 minus, let's see, x cubed squared is x to the 6th, and 2 factorial is 2, so I'm going to write 1/2 x to the 6th. Plus, now x cubed to the 4th is x to the 12th, and 4 factorial is 4 times 3, which is 12 times 2, 24. So 1 over 24, x to the 12th, and then minus 1 over, okay, what is that? It was 720? I think it's 720. 6 times 5 times 4 times 3 times 2, 720. So 1 over 720, x to the 18th, plus dot, dot, dot. So what we're going to do is we're going to integrate this, right? We want to find the antiderivative of that, the antiderivative of that, the antiderivative of that with respect to x. And so now we just use power rule. So I'm going to go ahead and write the antiderivative over here on this side. The antiderivative of 1 is x. The antiderivative of x to the 6th is 1/7 x to the 7th. So that becomes 1 over 14 x to the 7th plus the antiderivative of x to the 12th is 1/13 x to the 13th. So I have to hit that 24 with 13. That gives me 1 over 312. Do you have questions on where I'm getting these fractions from? I have one more to do. Minus, let's see, 1/19 x to the 19th, so 19 times 720. 1 over 13,680 x to the 19th power. Okay, and I'm only going to use the first 4 terms, so I'm going to stop there. Now that's my antiderivative. I need to plug in 0 and 1. So when I plug in 1, I get 1 minus 1/14 plus 1 over 312 minus 1 over 13,680. And when I plug in 0, I get 0, which is nice. So I'm just going to do this on my calculator. I'm going to get a decimal, and it's okay because I was asked to approximate anyway. Somebody please verify that I did this correctly. I got 0.9317, something like that. Anyone else get that? Close? 0.9317. Anyone else? Yeah? Oh, I know it's right. Okay. There you go. That's it. Quick question. What would happen if I asked you to integrate, not that, I asked you to integrate x times cosine x cubed instead? Wouldn't you do the same exact thing, except put an x here, right? Which would mean all of these need to get hit with an x, which means your next line, you just raise the powers on all these. And then you would integrate. Make sense? If I made that x to the 10th power, right? Then you would hit this with an x to the 10th. And so you'd raise all those powers up by 10. Does that make sense? The classic problem that students get is this one. You know, I could put limits of integration on here, but if I asked you to approximate this, you would first do the Maclaurin series for this, right? So you go to your table. Oops. Go to your table. E to the x is here. So we'd be doing, instead of x, we're doing negative x squared. So you'd replace all of these with negative x squareds. And then you'd figure out what it is, and then integrate each one. Questions?
Yeah, so real quick, we use the Mclaren series mainly when the x is about 0, right? And we use the Taylor series with anything else, you know.
So that's a great question. So when would you ever use a Taylor series, right? The thing is, it all depends on the interval of convergence of the series. So when you look at these, I keep hitting the wrong button. When you look at these formulas, look at your radius of convergence. This formula right here, do you recognize this one? This is that geometric series. This was 8.6. This was the formula from 8.6, where we took a function and we tried to convert it over to a power series. And it only worked if the absolute value of x was less than 1. So here, we had a very narrow window to look in, right? There's where you might want to do a Taylor series, because then you can move that window left and right. Now, I'm not going to test you on that, but we will use Maclaurin on e, sine, cosine. These are the most common functions that we'll be using anyway, because their radius of convergence is infinity. Doesn't matter where you center it. The sum infinitely goes forever in both ways, and we'll draw the whole function correctly forever. So it'll make the whole sine function appear. It doesn't matter where you center it. So let's center it at 0, because that's the easiest place to center it. Does that make sense? Christian, does that kind of make sense or no? Okay.
Yeah, it does.
All right. So there's another thing that I want to show you. And let me see if I can find this first. Let me close this, because I think that's what's causing the problem. See if I can find this. It's on YouTube. I haven't looked for it in many years. Bad math teacher. Let me see if I can find it. There he is. Worst professor. Let me see if I got to make sure this is the right video. This is not the right video, but it's the correct person. Maybe it's gone. Did they take it out? I'm a little disappointed. I know another way I can find it. Well, I don't want to kill any more of our time because we don't have a lot of it. If I find the video, I'll send it to you later. The video is of a professor who's teaching, I don't even know where, and it's like some engineering analysis class, or it's like some differential equations class. I can't even tell what it is, but he's working through a problem. And a lot of times as you go higher up, you'll notice this when you go to like big university, and professors will just like write their notes down on the board and just write, and all you're doing is sitting there copying, and it doesn't make a lot of sense. And they're just writing, they're usually writing their notes, like their notes on the board, and then they're just letting you go figure out how it all works. Well, one of the students raised their hand. They're like, can you show me how to go? Like there was something written, and then the next line, said equals, and then the next line, and the student asked, can you show me how to go from here to here? And the professor says, oh, you just divide. And the student's like, no, it doesn't work, and the math isn't right. And the teacher gets all kind of defensive and is like, no, you're just messing with me. Basically the professor's saying, he doesn't even really address the student's question. And the idea, if you get to the video, I'll try and find it. It may be gone now, but the whole idea is that the professor thought that the student was just messing with him because he thought the student should know how to do that step. And the student had no idea how to do the step and thought that the math was completely wrong. And so he was trying to call out the professor for making a mistake. In the end, the professor was correct. The student was wrong, but the way the professor addressed it really wasn't great. Okay, so you could look at it from two perspectives. What the student couldn't do is what I'm about to show you, all right? And this is a problem that is in our book. It's problems like this, okay? So let me just illustrate it with this example. It's not this exact problem, but it's the same principle. Let's take f of x equals 1 over cosine x, which we all know is just secant x, right? Find the Maclaurin for this. So there is no thing on your table for secant, all right? Now we could start by creating the list of derivatives, but that's gonna get really bad really fast. Do you all agree? Derivative of secant is secant x tangent x, and then derivative of that would be a product rule, and then we would have more product. It would be terrible, all right? So instead, we do know the power series for this, don't we? So we could rewrite this function like this. 1 over, what's the power series for cosine? 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial plus dot, dot, dot. So isn't that really what that means? 1 over cosine x means 1 divided by this. So you're taking the number 1 and you're dividing it by an infinite series. How do you do that, right? How do you do this? You don't just do 1 over this, 1 over, right? You can't do that. You have to do your favorite. Long division, okay? So on the outside, well, on the inside goes 1, right? That's what goes on the inside. And on the outside goes 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial plus dot, dot, dot. Now, our answer is going to be something with dot, dot, dots in it because this goes forever. But let's see how we would do it. Start with 1. What do you have to multiply 1 by to get 1? 1, right? So we put a 1 up here. Now that 1's going to go and hit everything here. Right? It's going to hit this, and then it's going to hit this, and this, and this. All those get hit, and then that goes underneath over here. So I put 1, then I put minus x squared over 2 factorial, then plus. Notice I'm leaving some little gaps in there just in case, because I have gaps in between the powers, right? What do you do once you put this line in? Subtract it, right? Or change the sign. So this becomes minus, that becomes plus, that becomes minus, that becomes plus, that becomes minus. And now you just add down, right? The ones go away and you're left with x squared over 2 factorial minus x to the 4th over 4 factorial plus x to the 6th over 6 factorial minus x to the 8th over 8 factorial. Is that okay? Now, what do you multiply 1 by to get this? That, right? So I need to put up here plus x squared over 2 factorial. And now here's where things start getting weird. I'm going to go x squared over 2 factorial times each one of these. So let's do the first multiplication. Here times here, that just gives you x squared over 2 factorial. But what about this one? Here to here. Will I get a plus or a minus?
Minus
Minus, okay. X to what power?
4th.
X to the 4th, but what's the denominator? It's 2 factorial times 2 factorial, right?
Would that be 4 factorial?
It would just be 4. It would just be the number 4. Because well, let's just write it. I'll write it. It's going to be a minus. It's going to be x to the 4th over 2 factorial times 2 factorial. That will turn out to be 4, okay? But I'm just going to write it as exactly what it is. It was the 2 factorial times 2 factorial. What would the next one be? What's the power? Well, it's positive, right? What's the power?
Would it be x to the 6th over 6?
Over 4 factorial times 2 factorial. I'm going to write it as 4 factorial times 2, and we will switch it in a second, okay? So that's this 2 factorial hitting the 4 factorial there. Let's do one more. Here to here, that'll be a minus x to the 8th over 6 factorial times 2 factorial. All right? We got to come through and change the signs. So that becomes minus, that becomes plus, that becomes minus, that becomes plus. And now the hard part, we got to add this down. Okay, so this right here, this is really, I'm going to have to do it to the side just so we have it. This is really x to the 4th over 4 factorial is 4 times 3 times 2 times 1. That's over 24. And then this right here is x to the 4th over 2 factorial is 2 times 2 factorial is 2. 2 times 2 is 4. So I need to put these together. So I'm taking negative x to the 4th over 24, and I'm adding to it x to the 4th over 4, which means I need a common denominator, right? So I have to multiply this one by 6 over 6. So I have a common denominator of 24. So negative x to the 4th plus 6x to the 4th, that should give me 5x to the 4th over 24. Do y'all see how that worked? We got to do that for this. We're going to do that for this. It's going to start to suck. I'm only going to do one more of these. So let's see. What is this next one? This one's going to be x to the 6th over, okay, what's 6 factorial? Did I say that was 720? It is, right? 720. And then this one is x to the 6th over 4 factorial was 24 times 2. I believe that's 48. Someone check me on that. And then we're going to put those together. So we're going to go x to the 6th over 720. That's positive. And then we're taking away x to the 6th over 48. Shit. Can I get a common denominator of 720? Yeah, I have to multiply the top and bottom here by 15. It just gets real messy with fractions. It's really what happens. And so I'll wind up with x to the 6th minus 15x to the 6th. That's minus 14x to the 6th minus 14x to the 6th over 720. And I believe that reduces, but I'll just leave it. I'm not even going to do the next one. This is going to be plus something. I don't even care. So what's the next number? Like what do I do next? I have to make that 1 become this, right? So that's what comes up here. 5x to the 4th over 24. And then I have to do it again. And do you see just how fast this gets bad? Like when I do my next multiplication here, here, and here, now these numbers are going to start to become pretty messy and hard to keep track of. Yeah. So on the test that I had given, the review, right? Where is this thing? On this review, I actually asked my student, or I'm asking you to do the first 3 terms of the power series for 1 over cosine. We just did that. We just did that problem. We just got the first 3 terms, didn't we? The first 3 terms are these 3. Now you can do this for all sorts of functions. Like you could do, like let's say you wanted to know the Maclaurin series for tangent x. I've got bad news. This is sine x over cosine x, which means you have x minus x to the 3rd over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial over 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And now you have to do long division with this x minus x cubed over 3 factorial here, and outside the 1 minus x squared over 2 factorial here. And then you have to start playing that game. What do you multiply 1 by to get x? And then you start working through it. That's pretty, it gets pretty bad. I mean, it gets pretty ugly, but that dividing using infinite series, dividing infinite series is a skill that you need to know to do later on in your life. Let me see if I can get this. We're out of time, pretty much. I really want to find this guy. I don't even know if I can share my audio. Worst teacher. Maybe it's just worst teacher, not worst math teacher. God, who knows what I'm going to get. That's him. I'm just afraid of what's going to come up on my screen right now.
Maybe if you click on the channel, it might have uploaded that other video.
Maybe. Where is he? Okay, let me see. Oh, here it is. Horrible teacher. Okay, now can y'all hear my audio though?
It seems that you're not happy.
No? Yes?
I heard it.
Happy.
Okay. It's really hard to understand him, but that's part of what makes him the worst or the horrible teacher.
It seems that you're not happy. You're not happy with the series. How?
Do you want me to translate? He just said, it seems that you are not happy. You're not happy with the series.
You multiply the series, but let's see now some other example. What I can do? Yeah.
Students asking, how are you going from the first line to the second line?
You multiply.
You multiply. Student says, can you show us exactly how?
Well, exactly how, let's see.
Just give it a second. Here it is. Looks like a Bessel function. Looks like a Bessel function because they use capital J here. You got infinite series, n equals 0 to infinity. You've got alternating x to the 2n, 2 to the 2n, n factorial, n plus 1 factorial, multiplied by x over 2. So, okay, let's see what he's doing. So the student's asking, he's checking to make sure his work's right, that he copied it from his work onto the board correctly, because I guarantee you the work in his hand is right, because it's been done many times, as you can tell. Here it is.
From here to here. Or you can divide one.
Okay, so from here to here, you just divide 1. That's what he says. Listen to the reaction of the students.
Well,
If you do it manually, it doesn't work. It doesn't make any sense.
okay, let's go further.
So he blows them off, right? The teacher blows them off. I don't agree with that necessarily, but the student doesn't know how to divide 1 by an infinite series, right? That's exactly what he couldn't do. Put it back up there, right there. So you have, see, it's 1 divided by x cubed, and then here's the infinite series plus dot, dot, dot. The professor just leaves the 1 over x cubed out here, and this right here, 1 divided by that becomes this, okay? That step from here to here is the long division I was just showing you. The professor's not going to show that step. He's going to assume, okay, yes, given enough time, you could figure that out, but the math is right. So this goes to here, and then the next step, you distribute through, and then once you're there, you can integrate it because everything's just boom, 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 right? So anyway, the moral of the story is that, if you have a professor that's obviously experienced, right? Most likely the math is right. So, if you're ever sitting there, don't be afraid to ask questions, but there's a chance that it's might be a hole in your math, right? So that's when you want to talk to your classmates and see like, hey, how did he do that? How did she do that? Whatever. All right, that's it. We're done. We're over time, and it's been an interesting semester, right? I appreciate your participation and keeping your videos on and everything else. It's been weird with this Zoom, but it is what it is. So hopefully we'll be on campus again soon. Are there any questions? No? What's happening next? I'm going to send you all